when talking about gases on a particle-particle level, particle-particle interaction, what we need to understand first is the postulates of the KM theory, kinetic molecular theory. And we find that there are 5 particular laws that govern the issues in the kinetic molecular theory of the particle level behavior. And I've kind of over the years used this little acronym, PAMVC. It's just stuck. You just learn it if you want to, or make your own out. But this is in order of presentation and importance of the postulates. P stands for particles. A stands for attraction, which is half of the phrase, attraction repulsion. Movement, velocity, and collisions. So, what these ultimately translate into, all matter is made up of particles. Particle-particle interaction is attraction or repulsion. All particles are in constant motion. All particles have a velocity or movement, velocity of movement, proportional to the kinetic energy content of the particles. Or velocity is proportional to kinetic energy. And collisions of particles are assumed to be perfectly elastic. I'll explain. That is, the sum of all the energy changes is equal to 0. Now, when particles collide, there is a heat loss, thermal change of momentum, and heat loss associated with the collision. But that's not taken into account because the net effect is that a quantity of gas doesn't lose enough energy to transition from, say, gas to liquid to solid and so forth. Like in this room, we're breathing air, and of course it's not transitioning out of its gas phase. So we assume that they're bouncing into one another, but the net energy change in those collisions is 0. Now what this leads to are some topics that we describe, how we describe behavior of particles. And those topics are theories. It's called the transition state theory, the 2 theories of particle interaction. First one, I should have said that one first. Collision theory. And the second one is the transition state theory. Now you'll see this come back up again in Chem 2 in kinetics. But anyway, the collision theory is the interaction of particles to form products. 4 events must occur simultaneously for reactants to form products in a chemical reaction. With another acronym of mine, spell the word CENT. You must have an effective kinetic concentration. Now what this means is if you have a reaction between 2 particles, A and B, producing products, A must be able to find B. If you think about it, if I had an A in, say, a box, this room, for example, I have an A particle A in one corner of the room and B in the other corner of the room, probability of A finding B is very low. But if I fill up the room with A's and B's, the probability of finding the other particles finding each other is increased significantly. That's what we're talking about, an effective kinetic concentration. So usually one of the reagents in, one or more reagents in a reaction is placed in the system in great excess, so that we can be sure that that particle reacts out and we get a stoichiometric yield out of the reaction. So that's one of the priority 1 issues in making products. You have to have the reactants be able to find one another. They have to have effective collisions, undergo effective collisions. And that is an orientation issue. On collision. Now, what that translates to, if you consider my hands as 2 different particles, they must come together like this in order to interlock. But if they bump into one another backwards or upside down, they don't come into, they don't bond and form the products you're trying to form. So there's just a certain geometry that is important when they connect that initiates the bond. And so you're trying to generate the highest probability of that. And I'll show you how that's done in just a minute. Nature. You have to have reactants in the system that will in fact react. So that's kind of a, okay, reactive reagents required. And you must have an effective activation temperature. Must have an activation energy, and the temperature, special temperature, pushes the reactants up to that, provides enough energy to push the particles up to a higher energy level, and at that point the particles interact and form products. Now, It is a plot of particle numbers versus their energy or velocities, either one being the same. So here's what you would expect in this type of curve. And there's a curve for each temperature effect, and it looks as sigma is the number of particles. And then you have your energy content or velocity on the horizontal axis. Now, at one temperature, say room temperature, I think we can all agree that this is filled with billions of air particles, and they have different velocities, some of them high, some of them low, or high energies and low energies. But if we plotted those energies against the number of particles, we'd find a trend that looks like this. Looks like a bell curve for temperature 1. We'll call that room temperature if you want to use a value, just to give an idea. Well, what the issue is that the majority of the particles fall along this high peak in here. And that's your average energy content of the particles. And it's usually a plus minus number that goes with it, like that. Now, what happens if you heat the particles? Well, some of the particles that are under this big curve will shift to the right. I'll use different colors in this. And you'll see a trend take place like this. You'll see a number of particles shift off to the right to a higher energy point, and that'll be T2. And if you continue to heat the quantity of particles, of course you would eventually get to where you're way down here, and they'll all go over to a higher temperature like this. Everybody's shifting to the right. Well, what's important about this is that down this field on the energy line, there is what we call a very special energy value called the activation energy. This is the point delta EA for any reaction. Every reaction has its own personal activation energy, and that's the energy at which the particles must be at in order to produce products. Any energies less than that, no reaction occurs. So less than this, no reaction occurs. Above this, yes, reactions occur. Now, the reason they occur is this is the energy content that provides the greatest probability of the four events coming together simultaneously. At delta EA, this is the greatest probability of reactants having sufficient energy for four reaction factors, is what they're called, occurring simultaneously. CENT issue, where all of these you have the best reactive possibility at the activation energy for the effective reactive concentrations, effective collisions. That's the main one. The more energy it has, the greater the interactions or the collisions, greater number of the collisions, and that speeds up the reaction. Of course, the natural interaction, and then of course the temperature is effective for that set of collisions. So that's what starts this. Out of this and comes several mathematical issues that are way beyond the scope of the course. But except we're going to give you two concepts that have evolved from this in terms of speed of particles and mass and temperature. First one is root mean square speed of the particles. Now, in the Boltzmann distribution, this would be that high point in the Maxwell-Boltzmann distribution curve. And it's given by symbology VRMS, called root mean square speed. As it shifts over, of course, that RMS is the average speed of all of the particles in this, or velocity, of all the particles in the system. And it's given by a very fundamental equation, and it's the square root of 3 RT over the mole weight, and it's usually published looking like that. Well, 3 and R are constants in here, so I converted those to a number such that when I multiply the number times the square root of T over M, we get meters per second, and all the problems in the book are in meters per second. So what I came up with is 158 on the square root of T in Kelvin over the mole weight. It's called the number average mole weight, is when you calculate a formula weight, and it's the number average. So if you wanted to calculate the RMS speed of O2 gas at 25 degrees C at 298 Kelvin, it would be given as velocity of O2 to equal 158, and the square root temperature would be 25 or 298 Kelvin. You don't even have to put the units in. And the molecular weight's 32, and everything's going to come out in meters per second. So that's the long and the short of this topic, is to apply this formula to, say, a given gas at a certain time. And all you need in there is the temperature and the formula weight, 32 grams per mole. And you don't need to put the units into, you're not going to cancel out, because I've already done that over here for you. And just tag it with meters per second. And that's the long and the short of that problem. Now, and you can change temperatures and particles and what have you, but that's what the issue is. Velocity of some particle is 158 square root of T over M in meters per second. So that's what you want to memorize and be able to, and the problems aren't going to be any more involved than that. Now, the second topic that comes out of this is what we call Graham's law of diffusion. Graham's law of diffusion describes the discharge velocity of a confined gas under pressure. Through a small opening. That is, if you had a cylinder of gas and you punctured it, what's the velocity of the gas coming out? Now, there are two types of problems here. One is a comparative problem, and the other one is a specific type problem. The comparative is based on velocity of effusion, the rate at which the gas comes out of the tank, is proportional to 1 over the square root of the mole weight. So if that's the relationship, what it's telling you is that the larger the see it's an inverse, the larger the mass of the particle, the slower it's going to move. So we increase the denominator, the velocity slows down, or emission or effusion velocity goes down. Now this also gives you an expression in relationship to the proportionality. It looks like this. Velocity of effusion is k times 1 over m, and again we get k to equal velocity times the square root of the mole weight and velocity of effusion. Now what this is going to lead to is a comparative analysis. Of effusion rates between two particles. So K would represent the effusion constant for, say, CO2, and you want to compare the effusion rate of SO2, for example. So you'd have a K for CO2, and that's equal to the K of SO2. So if K1, particle 1, equals K for particle 2, then in Vm, square root of m, you have the V particle 1, square root of m1 equals V2, square root of m2. This is Graham's empirical relationship, and it's a comparative analysis. Let me show you the problem now. We're comparing SO2 and CO2. I'm running out of time. Well, the formula weight of CO2, I think it's 32, 42, 44 atomic mass units. We'll just go with AMU. And the formula weight of SO2 is 64 atomic mass units. Now, when you have start with the Graham's expression, V1 and V2, we'll use this one as CO2, square root of mole weight of CO2. And this is velocity of SO2, square root of mole weight of SO2. You have two options to compare. So you're not solving for a given number in this per se number. You're solving for this one, CO2 is so much times faster than SO2, or SO2 is so many times slower than CO2. That's what I'm talking about in a comparative analysis. So if I solve for the velocity of CO2 in terms of SO2, I divide both sides by the square root of CO2, so which is velocity of SO2, square root of mass of SO2 over the square root of the mass of CO2. Or I would solve for the velocity of SO2 to equal velocity of CO2, square root of mole weight of CO2 over the square root mole weight of SO2, like that. So when we compare these out of the Graham's expression, you're really coming to figure this number times whatever the velocity is, number times the velocity. So this would equal the velocity of SO2 onto the square root of 64 over the square root of 44, and that's velocity of CO2, or velocity of SO2 is equal to the velocity of CO2 on the square root of 44 over 64. And then you work those down to the following. Let's see what that was. And it was at 1.2 here, reciprocal of that. And this one would be velocity of CO2 times 0.83. Okay, velocity of SO2, velocity of CO2. All right, you're comparing in one or the other. if you solve to this direction, what you're saying is velocity of CO2 is 1.2 times greater than SO2. SO2 is being the bigger particle. Or if you solve in terms of SO2, you can say the velocity of SO2 is only 0.83 of the CO2. So that's one type of problem you'll run into on the exam day. It'll have you a comparative set of like this. And all you do is just solve for one or the other based on the answer choices in the, down at the bottom, and solving this problem, putting in molecular weights and seeing who's going in faster or slower. Yes, ma'am.
How would the answers be written?
Which of the following would have the greater velocity, and how much is basically what they're saying.
Okay.
And you just look up, say they might have A would be 1.2, VS2, or B, and see it'll go down like that.
Okay.
So it's just a matter of a comparative number times the letter velocity, because you didn't calculate a real velocity in this context. Now, you can calculate RMS velocity if the problem gives you temperature up here, but that didn't give you temperature. That won't give you that. So it'll be in this context in the answer choices, if that's the question. Okay. The second problem is a more specific and includes a time factor. The diffusion time given N2 gas diffusion takes 24 seconds. How long will argon gas take under same conditions? From Grand's law, we have velocity 1 on the square root of mole weight 1 equals velocity 2 on the square root of mole weight 2. And our physics friends say distance equals velocity times time, like that. And if they're both under the same conditions, then distance, it means they're traveling across the same wall of the same container. And so we let that equal 1. And so the velocity factor is 1 over t, the time factor. And we substitute that into the velocity, and we get the time equation, square root of m1 over the time it takes for a fusion for particle 1 to equal square root of m2 over time for particle 2. And so in this particular one, for nitrogen, we got 28 grams atomic mass unit, square root, and it said it has 24 seconds, like that. Well, what about argon gas? What argon gas is 40 atomic mass units over X. And so you just have that relationship. So this is the time relationship, and then you have the just comparative relationship like that, unless maybe the problem will give you a velocity, and then you can do a specific comparison like that. But solving for X here, of course, that would be 24 times 40 over square root of 28, and everything comes out in seconds. And so that's a very simple finish to the kinetic molecular. Now there are, kinetic molecular theory is quite extensive. You can spend the rest of your life studying some of the stuff in there. But these are the only problems that will pop up on your exams.